we started section 10. We are still in section 10. So last time we introduced the general linear F test, this formula. We are going to continue to use it. So basically, you define a test statistic, call it F star, that equal to the SSE coming from the reduced model minus SSE from the full model, divided by the degree of freedom difference from the reduced model from the full model. So you don't have to actually come up with a degree of freedom for each model. Basically, this number is just the number of slope you want to test. This is the number of slopes being tested. Okay? Then the whole thing here divided by what you used to do, the SSE from the full model and the degree of freedom from the full model. So with this F test, this one under the null, it follows the F distribution. And the last time we give you an example to test one slope. And we also conclude that if you test just one slope, the t-test is equivalent to the f-test because the test statistic have the relationship. Let's say you are testing beta 1. Your t1 squared actually equal to the f star. That's the relationship between the two test statistics. And also the threshold you use to compare with for t alpha over 2 with the degree of freedom mu, square of this t equal to the threshold of f with alpha and degree of freedom 1 and mu. This relationship hold only if you test just one slope because, as you can see here, there's 1. This one coming from here, the degree of freedom difference between the two normal is 1. That basically tell you are testing just one slope. Okay? This relationship hold when the degree of freedom for f on top is 1, on bottom this is nu. This nu is the same as this nu. So this nu is the same as this nu. That's the degree of freedom coming from here. The degree of freedom for the full model. So don't try to generalize this relationship to multiple slopes. Only apply to one slope because there's 1 here. All right, so this is what we got from the previous lecture. Today we are going to look at the second example when you are trying to test all slopes. Let's say you have example with the same example with the 3 predictors. So the full model here is y equal to beta 0 plus beta 1, x1 plus beta 2, x2 plus beta 3, x3 plus epsilon. That's a full model. If you have a full model like this, you are trying to test all slopes. First of all, how do you write your hypothesis? That is beta 1, beta 2, beta 3, right? So you want to test if beta 1 equal to beta 2 equal to beta 3 or equal to 0. Your hypothesis alternative says at least 1 is not 0. At least one of the beta j is not 0 for j equal to 1, 2, 3. Okay? So what is the reduced model? This is a full model. What is reduced model? If you are trying to test all slopes, what is reduced model? You are going to assume, according to the null, all beta 1, 2, 3 are 0. So you basically have y equal to beta 0 plus epsilon. And following this, you have your full model, reduced model defined. You are going to compute the F star, fill in with all the SSEs. Then the test is easy. So for F test, we don't have 1 tail or 2 tail test. There's only one type test. You just compare your F star with the threshold F alpha. If it's greater, then you reject it. So use this formula to compute the F star. If F star is greater than F threshold alpha, reject it. But the point here is of course, if you use software, you can fill in both models. Use software to compute SSE for reduced model for the full model. It's a straightforward process, nothing to talk about, right? But there's something that data you try to derive from this outslope test. Basically, the SSE for the reduced model in this case, this is a topic we already covered in pre. This is your reduced model. What is SSE for the reduced model? We covered in the previous case, right? When you test one slope, you don't have a beta 1 times x1 or beta 2 times x. You don't have a predictor here. It's just the intercept and epsilon. In this case, what is SST for the reduced model? It equals to SST, right? Yes, it equals to SST. And this is a conclusion we already have. And also, you should know that SST does not vary with your model. The ST is the same for the full model or reduced model. Because in the formula for SST, you only just have summation yi minus y bar and square it. Y bar does not depend on your model. It's just summation y divided by n. It only has your observation in that. It doesn't have your model in that. All right. So in this case, what is the first term? SSER minus SSEF. So SSER minus SSEF. The reduced model SSE minus the full model SSE, it actually equal to you plug in SST minus SSE for the full model is what the same SSE we talked about before, right? It actually just equal to SSR for the full model. So eventually your F star here becomes what? On top, you have SSR you have SSR because on both top and bottom, we are talking about the full model. You can remove the R and F, just talk about SSR, right? This is SSR divided by what is the difference for here? This number of slopes you test, that's exactly P, right? Number of slopes you test is exactly P. So your F star become this divided by your SSE over the degree freedom n minus P minus 1. Okay, I'll talk about full model because we get rid of the reduced model from here. This is all from SSR, SSE, all for full model. So this one under null, we already plugged in what we mean by under null. This one follows F distribution with P n minus P minus 1 degree freedom. Right? Right again. So the F star, after you reduce that to this form, it follows F star with P and n minus P degree freedom. And this test is called the overall F test, also called Anovoa F test. So you may hear different names. If you take different class, this word is used a lot, Anovoa F test. So the overall test is to test all slopes if there's any one not equal to 0. So how come it follows F distribution? So this comes down to the definition for F distribution. So let's say we are talking about the full model. Let's know this already full model. SSR divided by the true variance here follows chi-square distribution with P degree freedom. The P here is coming from the full model, right? The SSE divided by true variance here, sigma squared, also follows chi-square distribution with the degree freedom of the regression model, minus 1, and minus p minus 1. That's the degree freedom for SSE. P is degree freedom for SSR. So in case of a simple linear regression, p equal to 1, you just have chi-square with 1 degree freedom. And these two are independent. That's also important. And SSR, SSE are independent. So follow the definition of F. We are going to do a ratio between this chi-squared variable. Basically, the first chi-squared variable, SSR over sigma squared, divided by its own degree freedom P on top, then SSE over sigma squared, divided by its own degree freedom. This is n minus p minus 1. Okay? To avoid confusing, I put that all in parentheses here. This is the definition of F. The ratio of two chi-square variables, each one divided by its own degree freedom here. And as you can see, the sigma squared variance canceled. Then you just have SSR over P over SSE over n minus p minus 1. That's exactly the formula, our F star, right? So this is how we come up with the F distribution with p and n minus p minus 1 degree freedom. Okay, so basically what I talked about for this section is just to prove why the F star you computed like this follows the F distribution with the 2 degree freedoms. All right, any question for this part? No? All right. So that's the overall F test or ANOVA F test. The third case is the general case when you test a subset of slopes. Test if some, but not all, some slopes are 0. Basically a subset. So let's say your null says, still coming from the same pool model, you assume that beta 2, beta 3 equal to 0. At least one of the beta j is 0 when j equal to 2 or 3. So how do you test if some of that is 0? We still use the general formula. We compute the F star. In this case, you first come up with your reduced model. If you're testing beta 2 and beta 3, beta 1 remain in the model. So y equal to beta 0 plus beta 1x 1 plus epsilon. That's your reduced model. Then you compute your F star, which is SSE for the reduced model minus SSE for the full model. What is degree freedom now at the bottom? It will be divided by the SSE of the full model over what's the degree freedom for each? What's the degree freedom for each? Can you come up with the degree freedom? Hello? What do you want to fill in here and here? Yes, but what is? Give me a specific number. 1. Again? We are testing beta 2 and beta 3 here. Yes, that's 2. How about here? How about here? What do you want to feel? It's n minus 4, n minus p minus 1. In this case, p equal to 3, right? This is a full model. You have x1, x2, x3, p equal to 3. So in the previous case, what is in the previous example, this is 3 and n minus 4, okay? In the previous case. In this case, this is 2 and n minus 4. So it follows F distribution with 2 and minus 4. Okay. So once you get this, you look up the table, find the threshold. So if your F star is greater than the threshold of alpha 2 and n minus 4, you want to reject? No. That's all it takes. All right. So to prove this thing follows F distribution is a kind of a more nested than the previous one. The Anovoa thing is relatively easy, so we don't require you to do that. Just use the formula given to you to be able to perform an F test. That is good enough. All right. All right. Next, I'm going to show that for all the 3 cases here, the general F test, the F star, can also be written in the form of R squared. Not just for the 3rd case, for all cases. Okay. F star can also be written in terms of R squared. So if you use the software to do the data fitting, some software will give you some squares, some software will give you R squared, some may give you both. So how you use that in order to solve your application problem, that should be something you learn from this class, right? You should be able to know how to interpret the data. So how do you express F star in terms of R squared? R squared could be given for you by the software, but how do you come up with your F test? So we do a few steps of derivation to basically convert the formula in the form of sum of squares to a formula in the form of R squared. So this is SSE reduced model, SSE full model over the degree freedom difference between the reduced model and the full model divided by SSE of full model. I'm writing this again, DFF. So each of SSE can be written as a difference between SST and SSR, right? SR reduced model. That's the first SSE minus the second SSE, that is SST and SSR for the full model. The degree of freedom difference between 2 models is P minus Q, because P is the degree of freedom, sorry, P is number of predictors for full model, Q is for the reduced model. So that is on top. At the bottom, you still write the SSE as the difference between SST and SSR. Okay, I need to move my equal sign to here. The formula gets too big. All right. Still, you should be able to recognize the formula, right? All I did is just to replace SSE by the difference of SST minus SSR. Then what is the SST cancel, right? Because SST is the same as SST no matter what model you use. So you basically have SSR for the full model minus SSR for the reduced model over P minus Q. And here you still have the same SST minus SSR for the full model and minus P minus 1. All right? Cancel the SST. Then you divide both by SST. What do you get? When you divide by SST, this becomes R squared for the full model minus R squared for the reduced model, P minus Q. This is what? 1 minus R squared for the full model and minus P minus 1. So if you use the software, you get R squared you can still come up with your IELTS test by plugging in the R squared like this. This should be relatively straightforward, right? It should be very convenient to use if you can automatically get your R squared from your software. All right. So in this case, this is a general formula. This is general. If it is overall test, yes.
What's P and Q again?
This is original R squared. Original, not adjusted. As you can see here, from this step to this step, all I did is to divide every sum squared by SST. That's original, not the adjusted. The adjusted one is divided by its own degree freedom. We didn't do that. Original R squared, okay? SST is the same for any model, no matter you use full model or reduced model. Keep in mind, that's the key here. All right, so next, let's say if you're testing for all slopes, for the overall test or the Anovoa F test. So in this case, the formula can be further reduced because your SSE are actually equal to SST, right? Your SSE are actually equal to SST. So SST minus SS, SSE are equal to SSE coming from here. So this is actually SSR over full model. Okay. Divided by SST, you get the R squared. So you basically get F star just equal to R squared F over P divided by 1 minus R squared F over N minus P minus 1. Okay. Sometimes I didn't put that, but that should be clear. So basically for the Anovoa F test, because you are testing for all slopes, Q becomes 0, and R squared R also 0. It should be easy to understand because your model does not have any predictor. The amount of variation in Y that can be explained by the amount of variation in X after you remove the effect of intercept. That is 0 because in the model you don't have X. So R squared R actually is 0. Okay, make this 0, make Q 0, you come up with this equation here. All right. Any question? No, everybody is good? Did I miss any question? Okay, got it. All right. So next we move on to section 11. Imagine this is in classroom. I probably have spread virus to so many students. All right. So next we are going to be talking about confidence interval for the mean response given a new data point at x0 and a prediction interval for y0 given a data point x0. X0, remember, this is not the first time we talk about this topic. This is for multiple linear regression. So f0 here is given as f0 for 1, f0 2, also with f0p. Excuse me, I need to drink some water.